All right, section 3.4. We're going to look at parallel and perpendicular lines together. So we have three theorems that are fairly straightforward. And I think if we draw pictures, it'll help us. If two lines are parallel to the same line, then they're parallel to each other. So let's draw this picture over here. Say we have line A, line B, and line C. So what this says is, if A is parallel to B, and B is parallel to C, those blue ones, right? Then, what do we know? A must be parallel to C. This is like the transitive property for parallel lines. So it's a shortcut in a proof in a way. Right? Instead of developing all those statements and reasons, we can use this as a reason unto itself. Next, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So let's take a look at this. We have A, and then I have line B, and line C. So what this one says is, if A is perpendicular to B, and A is perpendicular to C, so these guys are both perpendicular, what we know then is, then B is parallel to C. So they're parallel to each other. And drawing the picture, we can really see that. So B is perpendicular to A, and A is also perpendicular to C, so B and C must be parallel to each other. And the last one we'll be working with, in a plane, if two lines are perpendicular to one of two parallel lines, then it's also perpendicular to the other. Then we need to change a little bit. If a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So, see how this one works. A and B, and I have C. So this one states if A is parallel to B and C is perpendicular to A, and C is also perpendicular to B. We can use these as full-on statements and reasons. Next, I'd like you to go ahead and see if you can solve for the missing variable for each of these examples. Solve for each of these variables. Okay? Take a second, see how many of them you can do. We'll hook up on example 2 and I'll give you a few hints. So, we have vertical angles here, and we know that this is perpendicular, so that's 90 degrees. I'm going to set these equal to each other. Subtract 9 from both sides. X squared equals 81. So take the square root of both sides. X equals. Because that's the answer, right? There's two possible answers. Could x squared be negative 9? What's negative 9 times negative 9? 81. What's 9 times 9? 81. So there's two possible ones, and we don't know the correct one, right? Where that actually comes from is our difference of squares. So let me pause this, and I'll show you where. Here we go. So this next one, these guys are also complementary here. So x plus 62 equals 90. Subtract 62 from both sides. X equals 20 degrees. All right, so this next one, I'm going to go ahead and set these up. All right, hinge. How can we solve this? Elimination, right? That's why we worked on that solving system stuff in the last chapter. So these guys are linear pairs, so they're supplementary, right? So what I'm going to do is simplify each of these as much as I can, and see if I can set it up with elimination, or I can use substitution if I want. So I'm going to first subtract 10 from both sides here. And I get 5x plus 2y equals 170. This one I'm going to combine my like terms. Can I get 3x minus 30 plus 3y equals 90. I'm going to add that 30 to the other side. I get 3x plus 3y equals 120. So what I'm going to do to that one is I'm going to divide everything by 3. Right? I like to keep it simple, simplest form as possible. Right? The 3 can come out of everything. So I get x plus y equals 40. I'm going to take that, I'm going to move this on over here, and set up for elimination. What should I multiply that bottom one by to get an opposite? 2? How about negative 2? Right, because we want opposites with this positive 2 up there. If I multiply that by negative 2, it's negative 2x minus 2y equals negative 80. I'm going to put a little line through that just to know that I've taken care of that. And I'm going to add straight down this top guy and that bottom guy. So 5 plus negative 2 is 3x. The nice thing about those, positive 2, negative 2, they go bye-bye. And then 170 plus a negative 80. Divide both sides by 3. X equals 3. Then why not just use this guy right over here? Drop it in there. 30 plus y equals 40. Y equals 2. So it says, using the two diagrams, find the measure of the smallest angle. All right, well, let's plug this in and see if we can find the measure of all the angles. So 2 times 10, 20 degrees right there. So this has to be 160 degrees, because they're linear. And then we have 3 times 10 minus 20. That guy has to be 10 degrees. The smallest angle is 10 degrees, so that one is 80. Questions? All right. That's caught up. Next, suppose you plan to install molding on the sides and top of a doorway. You cut the ends of the top piece and one end of the side pieces at 45 degrees as shown. Will the side pieces of the molding be parallel? Remember, we like our doorways to have parallel edges, right? We like right angles and parallel edges. So one way to go ahead and ensure this is to set our cuts to be 45 degrees. Yes.
Why do we call it molding?
Or it could be trim or could be molded. I've heard it used both. So, magic of whiteboard. Ready? We want this piece to connect perfectly. Right. Perfect. So we have parallel sides. One way to do that, right, is to make sure that these guys are perpendicular. And in doing so, we can cut this at 45 degrees and this at 45 degrees. This at 45 degrees and this at 45 degrees. So now, how do I know that these guys are parallel? Since both the top and the sides are cut to 45 degrees, they sum to 90 degrees, making them perpendicular. Since both sides are perpendicular to the top, they are parallel to each other. All right, so a proof. The key to these type of proofs is to draw a picture. So let's draw a picture and see what we have here. All right, so in a plane, C is perpendicular to B. So I'm just going to draw C right here. And then I'm going to draw B. It doesn't really matter where we are, right, or how you draw it. I'm going to draw those and mark our givens. Next, B is perpendicular to D. Let's go ahead and draw in D. So we know it's perpendicular to B. B is perpendicular to B. Draw that next one in. And then D is perpendicular to A. So here's D in the green over here. I'm going to draw A in. All right, we have our little tool. So what I want to show is that A is perpendicular to C. All right, so let's do our two-column proof. Our statement and our reason. Right up here, I'm going to just put all of my givens all at once. C is perpendicular to B. B is perpendicular to D. D is perpendicular to A. That's a given. The next thing I'm going to show is that C is parallel to B. So C and B are parallel, obviously, right? How do I know that? Two lines perpendicular to the same line parallel. And then for the third reason, we proved that C is perpendicular to A, which we're trying to prove. If a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. So in this case, right, we have C is parallel to D, and D is perpendicular to A, so C has to be perpendicular to A as well. The last one says, could you also conclude that A is parallel to B? And looking at our diagram, A definitely looks parallel to B. So what is our reason? You definitely can. Since A is perpendicular to D, and B is perpendicular to D, two lines perpendicular to the same line are parallel to each other. And essentially what we're doing here, right? If they're perpendicular, we know they have corresponding angles that are congruent. Alternate interior angles that are congruent. They're all 90 degrees. Right?